Hi everyone, this is Lin Xiao. Today, I will present our work called Learning to Scaffold, the Development of Robotic Manipulation Skills. When we human beings encounter challenging problems, we are able to leverage the environment to ease various tasks. In order to build skyscrapers, workers leverage these scaffolds to temporarily support materials and get access to heights and areas. Parents provide training wheels to their children to help them learn how to ride bicycles. And in industry, workers use fixtures to guide the robots in manufacturing procedures. Our goal here is to construct a framework for robots to autonomously discover how to ease manipulation skill learning problems. We developed a learning framework for one robot to learn how to place the fixture optimally. Leveraging the fixture, the other robot is able to quickly master various manipulation skills, including peg insertion, wrench manipulation, and shallow depth insertion. Take the peg insertion task, for example. It is difficult to find reliable and accurate cues to guide the robot to accomplish a task precisely. However, if we have a fixture placed along the boundary of the hole, as shown in the slides, then the peg insertion task suddenly becomes quite easy, because all the possible motions of the peg are restricted by the fixture, and will only lead to one result, which is successfully insert the peg into the hole. As human beings, we know how to put the fixture optimally. But how can we train the robot to figure out the optimal fixture pose? In order to tackle this issue, we propose a framework containing two loops of learning processes. In the out loop process, the robot learns how to place the fixture. Once the fixture is placed, the robot switches from the out loop into the inner loop process, where it learns to accomplish the manipulation tasks using reinforcement learning algorithms. The accumulated reward is calculated to reflect the learning rate of the manipulation task, given the current fixture pose. The reward is sent to the out loop to guide the fixture pose selection problem. Here is an overview of our experiment setting. We have two robots. The left robot is holding the fixture and has the top view depth image as the input in the out loop learning process. The right robot is inserting the peg into the hole and has the RGB image as the input in the inner loop learning process. The accumulated reward of the right robot is used as a reward to guide the left robot to find the optimal fixture pose. We're formulating the fixture pose selection as a contextual bandit problem. The state is the depth image, the action is the fixture pose, and is continuous. And the reward is the inner loop accumulated reward. However, the reward function is discontinuous with respect to the action. In order to solve the contextual bandit problem with continuous action and discontinued reward function, we propose a smooth zoom-in algorithms. We first cover the continuous action space with a countable number of small covering boards with a given radius. Then we began to solve it as a multi-armed bandit problem. Once the ball is selected, we uniformly sample an action within the ball. In this way, we are able to smooth the continuous reward function. Meanwhile, the radius of the selected ball began to shrink. And it may lead to new exposure areas in the action space. We will initialize new covering boards to cover these new exposure areas. And we keep repeating the process until we reach the maximum number of iterations. We apply our framework on 3 challenging manipulation tasks, which are pack insertion, wrench manipulation, and shallow depth insertion. We plot the learning curves of the inner-loop manipulation learning process under optimal fixture pose, shown in orange line, and suboptimal fixture pose, and without fixture, shown in blue line. The orange line is always above the blue line, indicating the fixture would significantly boost the learning performance of these manipulation tasks. We also visualize the Q value of our out-loop learning process. These are 3 images of the Q value in pack insertion task. Each image represents the Q value and the various positions given the same fixture orientation of each image. The darker the pixel value is, the better the corresponding fixture position is. We also plot some fixture pose. You can see that all the optimal fixture poses are able to constrain the possible motion of the pack and significantly reduce the uncertainty of the environment. We first show the learning results without the fixture in the real-world experiments. You can see the robot failed to accomplish all the 3 tasks, indicating these tasks are really challenging. Next, we show the learning results with the help of the fixture in our learning framework. Our robot first samples fixture pose options and finds the optimal fixture pose position. Then, the right robot starts to insert the pack into the hole. In the wrench manipulation task, the fixture provides support for the wrench to stay horizontally, and it can apply a continuous torque to tighten the bolt. In the shallow depth insertion, the fixture restricts the translation and rotation motion of the pack during the insertion. So our framework is able to help robot autonomously discover how to ease manipulation skill learning problems. We apply our framework on 3 challenging manipulation tasks, which are pack insertion, wrench manipulation, and shallow depth insertion. Thank you for your attention.